All right, let's talk about something that drives AI developers absolutely crazy. How in the world can you take a massive AI model, delete 90% of it, and have it run no faster? At all? It sounds completely backwards, but it's a real and frustrating problem that people hit every single day. So we're going to get into exactly why that happens. So this really gets to the heart of the problem, right? On one side, you've got the research world, pumping out papers with these frankly unbelievable claims. They say you can get 80, even 90% sparsity. Sparsity, by the way, is just a fancy word for how many connections in the model you've zapped to zero. And the dream they're selling is beautiful. Smaller, faster, cheaper AI for everyone. But then you hit the real world. You talk to the engineers trying to use this stuff, and what do they tell you? Zero speed up, nada. Throughput is flat. And the cloud bill? Oh, that bill is just as high as ever.
So what gives? What is going on here? Well, the answer, and honestly the main takeaway for this whole explainer, is right here in this one sentence. Hardware executes kernels, not sparsity statistics. See, the chips themselves, the actual silicon, the GPUs, they don't read your research paper. They don't care about your pretty sparsity numbers. All they understand are kernels. Think of a kernel as a very simple, very specific command like multiply this chunk of data with that chunk of data. That's the language the hardware speaks. It's not interested in anything else.
Okay, so here's how we're going to break this all down. We'll start with the illusion itself, then get real about hardware. We'll talk about why structure is everything, how your compiler can secretly sabotage you, what we should be measuring, and then we'll wrap it all up with a new way to think about this whole thing. Let's jump in.
First things first, this sparsity illusion. Let's really dig into why 90% smaller on a spreadsheet doesn't mean 90% faster on a server.
I mean, the dream is just so appealing, isn't it? The academic papers paint this amazing picture where you can just chuck out huge chunks of your model and it'll still work great. It sounds like a total game changer. But then you look at the cold, hard data from people running these things for real, and the story is, well, it's depressing. Latency, the same. Throughput, stuck in neutral. And your cloud bill? Yeah, that's not going down either.
So we're back to that big question. Why? Why this huge gap between the promise and the reality? And look, it's not that the researchers are wrong about the accuracy. They're not. It's just that they're often looking at only one tiny piece of a much, much bigger performance puzzle.
And that huge missing piece, it's the hardware. This is where the beautiful theory of sparsity slams right into the harsh, unforgiving reality of silicon. And as you're about to see, different kinds of chips have completely different rule books.
Okay, this table lays it all out perfectly. Let's start with the big one. GPUs. These are the engines of modern AI. And what do they love? They love data that's neat, tidy, and packed together in dense blocks. If you just randomly poke holes in that data by sprinkling zeros everywhere, the GPU basically shrugs and processes the whole block anyway. It's just not built to skip around. Now, CPUs, they're a little more flexible. They can sometimes get a speed up from this random sparsity, but you need a ton of it for it to even matter. And then you've got your edge devices, right? The chips in your phone. They're so specialized, so locked down, that random pruning is a total non-starter. They only understand structure. And to really get why GPUs are like this, we've got to talk about tensor cores. Think of these as little super-fast math factories inside the GPU. Their whole job, their only job, is to do matrix multiplication, which is the heart of deep learning. But here's the kicker. These factories are set up like an assembly line. They expect neat, dense blocks of numbers, like an 8x8 grid, to come through. They are not designed to stop, look for a non-zero number, process it, then hunt for the next one. No way. They just want to chug through organized, predictable data. Okay, so if just randomly deleting stuff is a dead end, what's the alternative? Well, that brings us to the big idea, structure. Let's pit the two approaches against each other and see why structure always wins.
So on the one hand, you've got unstructured pruning. That's our randomly poking holes method. And the most important thing to see here is that the overall shape of the data doesn't change. It's still a big rectangle, just with some empty spots. But on the other hand, you have structured pruning. Here, you're way more deliberate. You're not just deleting random numbers, you're lopping off entire rows, or entire columns, or big chunks. And because of that, you are actually making the matrix smaller. The shape itself changes, which means there's literally less math to do.
Here's a great way to think about it. Imagine unstructured pruning is like getting a giant textbook and a black marker. You go through and cross out random words on every page. Now, if I ask you to read what's left, what do you have to do? You still have to pick up that heavy book, turn every single page, and scan the whole thing with your eyes just to find the words that aren't blacked out. The total amount of work is pretty much the same.
Now compare that to structured pruning. This is like taking that same textbook and just ripping out entire chapters. Boom, chapter 5, gone. Chapter 12, gone. Now the book is physically smaller, it's lighter. When I hand it to you, you can just skip right from chapter 4 to chapter 6. You've saved real time because the job itself actually got smaller.
And that brings us to a super simple, super powerful rule of thumb. If you walk away with one thing, let it be this. If you don't change the shape of the tensors, those big blocks of data, you're not going to change your throughput. It's really that direct on today's hardware.
Okay, so we're all on board, right? Structure is the answer. Well, not so fast. It turns out there's another villain in this story, a hidden bottleneck that can ruin everything, and that's the compiler.
So the compiler is basically the translator between your high-level code and the low-level language the GPU actually speaks. The problem is, this translator might not know the special words, the sparse kernels, needed to tell the GPU to skip the empty parts. Or, and this is the really infuriating part, sometimes the software will look at your perfectly structured, sparse matrix, and it will helpfully fill all the empty spots back in with zeros right before sending it to the chip. It completely undoes all your hard work.
So with all these traps, the hardware, the compiler, what are we supposed to do? Well, it means we need to change how we measure success. We have to stop obsessing over simple sparsity numbers and start measuring what actually matters.
So instead of just proudly declaring, my model is 90% sparse, researchers need to start reporting things that an engineer would actually care about. Like, what's the real wall clock time it takes for the main kernels to run? How many of those big matrix multiplications, the gems, are you really doing? How much memory are you hogging? And for language models, the killer metric is tokens per second when you have just one user, like in a real chatbot.
And what do all these new metrics have in common? They force you to look at what the hardware is actually doing. They connect the abstract world of theory to the concrete world of performance. In fact, here's a simple experiment anyone could run. Take a model, prune it to 80% with a random unstructured method. Then take the same model and prune it just 30% with the smart structured method. Now, forget the sparsity numbers. Just put them on a real GPU and measure the latency. Measure the actual speed. I promise you, the results will speak for themselves.
Okay, so this brings us to the big finale. We need to completely reframe how we even think about this problem. It requires a whole new mindset. When you look at what actually makes a model fast, the model itself, the pruning algorithm you used, that's maybe 20% of the equation. The other 80%, that's all hardware limitations and compiler weirdness. If you're only focused on that first 20%, you're just never going to win.
And it all comes back to that one core idea. I'm going to say it again because it's that important. If your pruning doesn't change what the hardware is doing, it doesn't change performance. Full stop. It really is that simple.
And that leaves us with this final, powerful thought. For so long, we've all been treating pruning like it's a math problem, an algorithm problem. But it's not. It's a systems problem that's been masquerading as a model problem. It's about the whole stack. The algorithm, sure, but also the compiler, the software, and the physical chip itself. And once you start thinking about it that way, well, that changes everything.